So, now of course, you have some fluid in between the plates, right, because these two plates are immersed in a bath of electrolyte. Okay, there is fluid in the outer region as well as inner region, and if we assume that the plates are in equilibrium, what you could do is you can think about doing a force balance. So, you can consider a volume element of fluid, okay, that is parallel to the face of the plates that are considered, and you could do a force balance. Okay. It turns out that there are two forces that are acting on the volume element. First is what is called as osmotic pressure force, and this arises because if you look at the region within the two plates, there is certain concentration of electrolyte, and because of the fact that there is a concentration of the counter ions close to the surface is higher, right. So, the concentration in this region would be very different from the concentration in a region that is in the region outside the gap. Okay. That is the concentration of if I were to think about the concentration of the electrolyte in the region as C1, and if I say that the concentration of the electrolyte in the region outside the plates is C2, okay, the C1 would be greater than C2, okay, because of the fact that the concentration of the because of the fact that the gaps are low, and if you look at the number density of ions in the gap would be larger compared to what you have in the region outside, okay, because of this difference in the concentration of ions in the region between the plates and that outside, there is going to be an osmotic pressure force term that is going to be important. And the second force will arise because of the fact that you have particles that are charged, and because of this there is going to be an electrostatic force that will also come into the picture. Okay. So, what we are going to do is we are going to consider the x component of the two forces. Okay. The x component of the osmotic pressure force is given by minus dP by dx. Okay. That is because we are only considering a one dimensional case of how the force varies with distance in the x direction, okay, and Fx is given by minus dP by dx, and the electrical force per unit volume is given by the product of charge density times the field strength. Okay. That again comes from the electrostatic concept that electric field E is force times Q, and E again is minus d psi by dx. Sorry, this is F times Q, right. So, this is F is E times Q, and therefore, I can write F as Q times E, that is Q times d psi by dx, and there is a minus sign here. So, therefore, one could write the electric force per unit volume that is acting on a fluid element that is considered is given by the charge density rho star times the gradient in the potential. And because the plates are in equilibrium, the summation of all the forces should be equal to 0, that is Fp in this case Fx, right, plus Fel would be equal to 0. Therefore, dP by dx plus rho star times d psi by dx is going to be 0. You can arrive at a similar expression for the force balance if you start with Navier-Stokes equation as well, and this is the term that comes if you have flow in the solution, right. However, because we are talking about a case where you have particles immersed in a infinite bath of electrolyte and there is no bulk flow, the velocity u is going to be 0. Therefore, this term is going to be 0, and we are going to assume that the gravitational effects are not important. Therefore, that term again would be 0, and you have the charge density here times E, that is the strength of the electric field, and that we know it is minus d psi by dx, and you have delta p here, and because we are only worrying about the pressure gradient in the x direction, therefore, this del p essentially will be dp by dx. Okay. So, whether you identify the different forces acting on the volume element and then do a force balance, or you start with Navier-Stokes equation and then cancel out neglect the terms that are not relevant, you end up with the same expression that this f x plus f E L is equal to 0, right. So, therefore, the criteria for the equilibrium is f x plus f E L is equal to 0. Therefore, dp by dx plus rho star times d psi by dx is equal to 0, and we know this from the Poisson equation, right. The Poisson equation in one dimension is d square psi by dx square is equal to minus rho star divided by epsilon. So, I can, instead of rho star, I can replace. So, that is the dp by dx term. Instead of rho star, I can replace that with epsilon, right, times d psi by dx and d square psi by dx square times d psi by dx. Since we know that d square psi by dx square times d psi by dx is equal to 1 by 2 d by dx of d psi by dx whole square. So, if I simplify this, what I get is 1 over 2 times d by dx of d psi by dx whole square is 2, okay, is 2 times d psi by dx times d square psi by dx square, right. This gets cancelled, so you essentially end up with the same term. So, therefore, dp by dx minus epsilon times d square psi by dx square times d psi by dx, I can write this as dp by dx minus epsilon divided by 2 times d by dx of d psi by dx whole square, right. So, if I take d by dx is common. So, therefore, this becomes p minus epsilon by 2 times d psi by dx whole square is equal to 0. Now, if I integrate this, so what I end up with is p, that is this, minus epsilon by 2 d psi by dx whole square is equal to constant. Okay. And so, therefore, the criteria for equilibrium now becomes p minus epsilon by 2 d psi by dx whole square is equal to constant. And now, if you look at this expression, this is the contribution that comes from the osmotic pressure, and this is a contribution that comes from the electric field. Okay. So, what this expression essentially tells you is that if you look at not only for the volume element, like say at the central location, if you look at volume element at any location, the this equation would be satisfied because of the fact that we are assuming that the entire system is in equilibrium, and the electric field contribution to the pressure is what is called as a Maxwell's pressure or the Maxwell stress, which comes into picture whenever you have flow or maybe a flow coupled with electric field effects in the solution, or any case where you have pressure contribution comes from things like osmotic pressure or flow and then there is a coupled effect along with the electric field present in the system. So therefore, this expression that we have derived, which is the condition for equilibrium, is valid at all location within the plates. So, of course, we will be interested to find out what is the integration constant. One of the way to think about obtaining the integration constant is to look at how does this potential, because of the overlap, varies with the distance, right. So, if you look at this, I can say that at the midpoint, so if h is the distance between the plates, okay, and that is the dashed line that is drawn, that is the mid plane, that is at the distance h by 2. At the midpoint, you can say that d psi by dx is equal to 0, okay, at h by 2, okay, and pressure at h by 2 is p h by 2. Okay. So, therefore, if I substitute these conditions, this term becomes 0. Therefore, constant essentially becomes p at h by 2. Now, if you look at the overlapping electrical double layers, so even though the surface potential is psi naught, okay, when the overlap occurs, okay, when the overlap occurs, let us say that this is the potential with respect to one plate, okay, and say that this is the potential with respect to other plates. So, the repulsion between the particle does not depend on what is psi naught, however, what is the potential at the overlap. Okay. Therefore, psi h by 2 is the potential that governs the repulsion between the surfaces, not psi naught. Okay. So, therefore, now we would like to express the potential, the so what we will do is we will again do some simplifications. So, that is the force balance, and therefore, I can recast this as dP is equal to minus rho star multiplied by d psi, and we know that the charge density in solution can be written as summation I Z I E times N I. So, all that we are doing is we are summing up the charge contribution because of different types of ions in solution, right. So, that Z I is the valency and E is the charge on the electron, and N I is the concentration of the ith type of ions in solution. So, I can bring in the Boltzmann factor. So, Z I E times the Boltzmann factor, right, that is rho star, and when you have Z is to Z electrolyte, Z I takes the value of plus Z or minus Z. Therefore, I can expand this term, okay, I can write two terms, one for the plus Z case and the other one for the minus Z case. Therefore, dP becomes minus Z E n infinity times, okay, and now note that N I infinity, I am replacing that as n infinity itself, because the concentration of both the cations and the anions is exactly same, and I can denote that as n infinity. So, therefore, I can take this out, that is a common factor. So, you have exponent minus Z E divided by k B T minus Z E n infinity times exponent minus Z E psi by k B T minus exponent of Z E psi divided by k B T. Okay. So, that is what you end up with. and we can use the fact that exponent x minus exponent minus x is 2 sine hyperbolic x. Therefore, I could write this as dp. So, I think there is a mistake here. So, that should be positive. Okay. Therefore, dp is equal to 2 times z e n infinity times sine hyperbolic z e psi divided by kbt times d psi. I could integrate this and use the boundary condition that in the so when we consider that the potential is at a very large separation at a very large distance from the surface, we know that the potential would be 0, that is psi is equal to 0, and at that location we say that the osmotic pressure which is proportional to the concentration of ions that you have at that location is P naught, and at h by 2 the potential is psi h by 2, and correspondingly the osmotic pressure P is P at h by 2. Okay. Therefore, once I integrate and then substitute the these conditions, I end up with P h by 2 minus P naught is equal to 2 times kBT n infinity, and you have cos hyperbolic z e psi at h by 2 divided by kBT minus 1. Okay. So, this expression essentially gives the excess pressure, okay, that is P h by 2 minus P naught. P naught is the osmotic pressure where psi is 0, and the difference between P at h by 2 minus P naught essentially gives you what is the excess pressure at x is equal to h by 2, and it represents the force per unit area with which the plates are pushed apart because of the overlap. Therefore, P h by 2 minus P essentially is Fr, that is the force of repulsion, and that is the force of repulsion per unit area, and that is what is given by this. Okay. So, therefore, what we are trying to do here is that if you look at this expression f of Fr, which is the force of repulsion, it is expressed in terms of the potential at the midpoint. Okay. That is, it is expressed in terms of psi at h by 2, that is the potential at the midpoint between the two plates, and of course, this is an unknown quantity. What we know is psi naught. However, psi at h by 2 is not known, and you can do some approximations to find out to evaluate what is psi at h by 2. So, that is the excess pressure Fr. Now, we did think about some special case of Gouy-Chapman expression, which is applicable for Z is to Z type of electrolyte for any surface potential, right. So, now if you look at this expression, we derived this for a case where the potential has fallen to a low value. That means, we are talking about a distance at a distance that is sufficiently okay. So, we are talking about the case where we are looking at a distance a very large distance from the charged surface, such that the potential has fallen to a low value, right. So, in such a case we can simplify gamma is equal to gamma naught exponent minus kappa x as psi is equal to 4 kBT divided by Z e gamma naught times exponent of minus kx. So, what we are going to do, so because we have two plates, plate 1 and plate 2, so therefore, there is going to be psi 1, that is contribution that comes from the plate 1, and psi 2, that is a contribution that comes from the psi 2. So, we are going to say that psi at h by 2 is summation of psi 1 plus psi 2. Therefore, psi h by 2 becomes 2 times 4 kBT divided by Z e gamma naught exponent of minus kappa h divided by 2. Okay. So, this particular approximation is what is called as a superposition approximation, which is valid only when the surfaces are sufficiently far apart. Okay. That is what I mentioned, that the Gouy-Chapman theory was simplified, okay, to give this expression, which is applicable for any psi naught. Okay. The psi naught could be very high, however, which is valid only when the surfaces are sufficiently far apart, that is, we are considering a case where the overlap of the double layers is moderate. So, therefore, psi h by 2 we have derived that, so this result that we have used, it applies well away from the surface where the potential is low, right. And we can of course consider the fact that the cos hyperbolic that you have here, right. So, if you look at the expression for the excess force, I have a cos hyperbolic term, and I can I can consider a series expansion of the cos hyperbolic term, and the excess pressure now I can write this in terms of I can neglect the higher order terms, and therefore, so instead of cos hyperbolic, what I can do is I have 2 times kBT, this term, instead of cos hyperbolic h by 2 kBT minus 1, what I will do is I can take this, it is cos hyperbolic x minus 1 is equal to x square by 2 factorial, and I am going to neglect the higher order terms. Therefore, so I can write this as this divided by 2, right. Therefore, this gets cancelled. So, I essentially end up with this expression. So, therefore, Fr, which is the force of repulsion, goes as kBT times n infinity Z e psi at h by 2 divided by kBT whole square. So, I can take Z e divided by kBT outside, and I have psi h by 2 square here. I can replace for psi h by 2. Okay, I can replace this expression now. Therefore, Fr, that is the force of repulsion, essentially becomes kBT n infinity. So, I have 8 gamma naught exponent of minus kh by 2 whole square. That means the force of repulsion essentially becomes Fr is equal to 64 kBT n infinity gamma naught square exponent of minus h by k inverse. So,